Buenas noches, good evening, everybody. Welcome to day one on week 14 of the semester. We only have a few more weeks before we end the semester. A couple of announcements before we get started. Remember, today is the only day that we will have class because on Thursday is Thanksgiving, so we will not have class. In addition to that, be mindful that when it comes to the schedule, we have a special assignment that is my favorite molecule project. This week, I will be putting a document together of what you guys have to actually submit to me. We are not going to have presentations in class, but you guys need to complete the assignment because it's part of the grade for you guys in this course. Now, that assignment is going to be due the last week of classes. And in general, you just have to pick a molecule and answer a few questions that I'm going to put in the document. So next week, when we come back after Thanksgiving break, I will just give you guys a little introduction on what is expected for you guys to submit. But from here to the end of the semester, we are just going to be doing our regular class. We only have 3 more weeks of classes after this one. And in general, what I'm going to be asking for you guys to complete in lab is going to be the experiments that we have scheduled from the lab kit. So be mindful of that. There are some labs that were on the schedule that we will not be performing, but I'll give you guys a reminder of that as the weeks progress until the end of the semester. So taking that into account, the last thing that we talked about in class was naming acids and bases. We learned how to go from chemical formula to name and from name to chemical formula for acids. We concluded the naming of bases, as you can see here. And now we are going to proceed to specifically focus on acids and bases based on the Bronsted-Lowry definitions for them. Now, as you can see here in the middle, the Bronsted-Lowry theory or the Bronsted-Lowry definition for acids and bases is the one that is the most commonly used in both chemistry and biology, which states that an acid is going to be a proton donor. And understand that proton is just another word that we utilize for the hydrogen ion. Give me one moment. Sorry, you guys, I was just sneezing. My allergies are a little bit active today. But getting back to this, so an acid is going to be a proton donor, and remember that a proton is going to be specifically an H+. Is another, we can also call them hydrogen ions. And then the base specifically is the molecule that is going to accept that proton. Here we can see ammonia, which we learned last week that it is a weak base. And we have a molecule, for example, water. Water can act as an acid or it can act as a base. There are very few molecules that can actually accomplish this, but a molecule that can act as an acid or a base, this is known as an amphoteric molecule, okay? Let's see some examples of reactions so we can see this dynamic of what is an acid and what is a base. Now, here we have specifically the reaction with HCl is reacting with water to make the hydronium ion and the chloride ion. We can clearly say And by looking at the labels that we have, that HCl is acting as an acid, meaning that it's going to be a proton donor. Because when we look at the product of the reaction, once HCl has lost that hydrogen, it becomes Cl minus. In other words, the chloride ion. Now, water in this case acted as a base and is going to accept a proton. Let's notice that when water does this, we are going to increase the number of hydrogens that water has. And in addition to that, the formal charge for the water has also changed. So water is a neutral compound when it accepted that H plus. So it gained H plus. Not only we see that we go from H2O to H3O, but in addition, we can see that there's a change in the formal charge. In this course, specifically, we don't dive into how do we know what is the formal charge for a compound. Those rules I will give to you guys in a few moments, so you don't have to stress about, okay, how do I know that it is plus, minus, so on and so forth. Similarly, with the chloride ion, why is it negative? I will explain it in detail in a few moments. Now, as you can see, the reactant side, which is to the left of the arrow, are labeled acid and base. We have names for the components of the product. Now, the compound that is formed from the base accepting that proton, that is known as conjugate acid. The ion compound that is made from the acid losing a proton is known as a conjugate base. So even though it may be a little bit counterintuitive, understand that an acid is going to create the conjugate base. So it's going to be opposite. The acid creates the conjugate base. Then the base is going to create the conjugate acid. And that pairing is always like that. The acid creates the conjugate base. The base creates the conjugate acid. Now, here we have another example of an acid-base reaction, okay? Or a Bronston-Lowry acid-base reaction. In this process, we see that ammonia is acting as a base, and then water is acting as an acid. So in this case, we can see since ammonia is acting as a base, in the product side, we go from H3 to H4, because remember that it gained an H plus. Water, since it's acting as an acid, we can see that it lost an H plus. So it goes from H2O to only one hydrogen. Okay? And we can notice that there's some form of charge attached to it. Now, let me ask you guys this. NH4 plus, is that the conjugate acid or conjugate base in this reaction? What is the label that we are going to utilize for NH4 plus? Conjugate acid or conjugate base? Thank you, Maria. Exactly. This is the conjugate acid. And its NH4 plus is the conjugate acid. That means that the hydroxide is specifically the conjugate base. Now, when it comes to all this process, I want you guys to be able to write the chemical formula for a conjugate acid and conjugate base, and we're going to practice that in the problems that I have on the left side of the slide. But if I give you a chemical reaction, I want you guys to be able to identify, okay, this is the acid, this is the base, this is a conjugate acid, this is a conjugate base. So let's first get started with, if I'm giving a molecule, can I write what is going to be the conjugate base that comes from it? So in this problem, as you can see, the instructions say, give the conjugate base for each of the following Bronsted-Lowry acids. So understand that if something is an acid and is going to form a conjugate base, overall is going to lose an H plus, only one hydrogen, okay? Now, these are the rules for specifically the formal charge that they're going to adopt, okay? Let's say that my acid is neutral, okay? Like we can see here on problem 1, 3, and 4. If it loses an H plus, that means that the conjugate base is going to have a formal charge of -1. Okay? If my acid is actually +1, like we have an example number 2, once that +1 leaves, because remember that the protons are +1 charge, then that means that the molecule that we're going to write is going to have a formal charge of 0. Remember that you will always are going to write one less hydrogen in that chemical formula. Let me just add one more example to this. Let's say that we have H2PO4 -1. Specifically, this is dihydrogen phosphate. Now, if my molecule starts with -1, okay, and it loses a hydrogen, then it's going to get a -2. And as you guys can see, what's happening overall is that we are just going to change that form of charge, okay, into, if you lose a hydrogen, then you're going to be more negative. So if we utilize like a number line method, just for those students that maybe the numbers are not making sense, let's say that we have a number line. And this is representing the formal charges. If we have the values of +1, +2, 0, -1, -2, let's even go to -3. What is happening overall is that we are just changing 1, okay? So if you start at 0 and you lose a proton, then you become -1. If you are +1, let's say that we start at +1. Again, if you lose a hydrogen, you become 0. If you are +2, you lose a hydrogen, your formal charge becomes +1. And you guys can see that there is a trend. So let me do the first problem with you guys. We have HI. If I'm trying to write the conjugate base, meaning HI is acting as an acid. What kind of acid is HI? Is it strong or weak? Let's put it in the chat. It is an acid, but is it strong or weak? Thank you, Katie. Yes, it is a strong acid. So When we are writing the conjugate base, meaning that HI already lost the proton, so minus H plus, then the chemical formula that we will write is just iodine, right? Because we lost a proton. Its formal charge after losing the proton is going to be -1. Because as you can see here, let me use my highlighter tool. It started at 0, it lost a proton, so it became -1. So we started at 0, right? We lost a proton. So that's how it converted to -1. So let's do step by step. If I start with NH4 plus and I lose 1 hydrogen, what would be the chemical formula without putting a formal charge in it? So I go from NH4 to what chemical formula if I lose a proton? Excellent job. We go to NH3. Now, if I look at what happens overall, in terms of the formal charge, I was a +1, and because I lost a proton, what is going to be my formal charge? So I started at +1. What is going to be my formal charge? Excellent, 0. Great job, you guys. Now, the formal charge of 0, we don't even write it in. We just leave the chemical formula alone. Let's go to example 3. We start with H2CO3. So when carbonic acid acts as an acid, the product of carbonic acid losing a proton and making, a conjugate base, what would be the chemical formula? When we lose an H plus without the formal charge, what would be the chemical formula? Great. HCO3. Now, if we follow the trend, whichever works for you, either the one that I wrote or the number line, what would be the formal charge of HCO3? Knowing that starts at 0. Excellent. Thank you, Vanessa. Yes, it's going to be -1. You can write negative or -1. Make sure that you pay attention to the instructions that will be given to you. Because remember, next week we have an exam. It's going to be the last midterm before the final. Let me see if people are getting the hang of it. What will be the chemical formula and overall charge for the conjugate base of HNO3? Let's put it in the chat. Great. It's going to be NO3 -1. What about, for example, 5? Well, it's going to be the chemical formula and overall charge for the conjugate base of H2PO4. Excellent. Thank you. HPO4 -2. Okay. You may be wondering, why is this important? Because overall, we have to identify which compounds are going to be acting as acids. And if we see them in a reaction, we need to be able to recognize, oh, okay, this acted as an acid and this is the conjugate base that is going to be produced. Let's now actually go the opposite route. If I give you a base, let's write the conjugate acid. So the following are conjugate acids. Sorry, we need to write their conjugate acids. They are bases, okay? So if we have a base and we need to write the conjugate acid, understand that we're going to add an H plus. So all of the chemical formulas that we see in 1 through 4, basically we're going to add a hydrogen, okay? Now, how does that affect the formal charge? Let's understand that when it comes to these formal charges, if your base starts at -1, when we add a proton, the formal charge becomes 0. If your base has a charge of -2, it's going to become -1. If your base is -3, it's going to become -2, because we're adding a positive charge overall to the molecule. So that's why we have those changes. In addition, if your molecule overall is 0, then it's going to change overall to a formal charge of +1. So if we do the number line, for those of you that maybe the number line helps, let's just write a few numbers. Let's say that we have -1, -2, -3, 0, +1, +2, +3. You can see here that now the transitions are going to be, okay, if I'm standing here, then I'm moving towards the right. So I go from -1 to 0. We can only go one at a time because we're only accepting one H plus, okay? That's why we cannot do the jump from -1 to +1. We're only accepting one H plus. If you are at 0 and you accept the proton, then you become +1, and so on and so forth. Remember, what I'm outlining here in the number line, this is going to be the formal charges, okay, that are going to fluctuate between the base and the conjugate acid. So I'm going to do number 1 with you guys. So we can see that it's CN-. Whenever we're writing the conjugate acid for a particular base, let's actually understand that the hydrogen is going to most of the time be added in the beginning or at the end, depending on the atom that we're talking about. So here we have CN-, that's cyanide. Now, let's understand that overall, what's happening here is that we're going to write HCN as the chemical formula for our conjugate acid, okay? In this case, we're going to put specifically the H in the beginning. Understand that traditionally, because of the attachment of the atoms, if your chemical formula has an oxygen, then the hydrogen goes next to the oxygen atom. So for example, for O2-, we write OH, and what's going to be the formal charge of that OH? Great job, -1. The formal charge of HCN is 0 because remember, it started at -1, and then when it accepted that proton, it became 0. So that's why HCN doesn't have an overall charge. And we don't write in the 0, okay? When we write the chemical formula. Now, in H3COO, okay, which that is the acetate ion, let's understand that similar to example 2, we are going to place the hydrogen next to the oxygen atom, okay? And it's particular like for those 2 examples because technically, if we have like sulfates or phosphates, that is not the case. So it's basically examples like this, the O2 or CH3COO, okay? It's only those 2 cases that we put the H at the end. So for the chemical formula, we're going to write CH3COOH. Now, what's going to be the formal charge of CH3COOH? Great job. Exactly. 0. Okay. Let's do one more. What about if we have NH3, what's going to be the chemical formula and formal charge of the conjugate acid of NH3? Great, thank you guys. It's NH4, and the formal charge is +1. Remember, whenever we are writing the conjugate acid, we're only going to add 1 hydrogen to the system, okay? Any questions on writing the conjugate base given an acid or the conjugate acid given a base? Then let's move on to identify if we are given a reaction, what is the conjugate, what is the acid, the base, conjugate acid, and conjugate base, okay? So letter A is already given on the slides. In this, we can see, since specifically NH3 went to NH4 plus, this is acting as a base, this is acting as an acid, this is the conjugate acid, and then this is the conjugate base. Because we can observe that H2O lost a proton, okay? Let's look at example B. We see that we have water, we have HCO3, all of a sudden we make CO3O2 negative, and we make H3O plus. So what is the role of the water in this system? Is it an acid or is it a base? Excellent. This is acting as a base. The reason why we know it's acting as a base is because we can see here that it accepted or gained H plus. So what will be the label immediately that we put on that H3O plus? If water is the base, is that a conjugate acid or conjugate base? Great job, you guys. Conjugate acid. So if water is the base, then immediately HCO3, this is going to be your acid. What's going to be the label of that CO3 2 negative? Great job. This is the conjugate base. Let's just do one more example. What's the role of NH3 in this reaction? Let's observe what's happening overall. Great. This is a base. This is the acid. Once you identify the base, then you know that the other one is the acid. What is the label for HSO4 negative? Is that a conjugate acid or conjugate base? Great. You guys got a hang of it. Awesome. This is your conjugate base. This is the conjugate acid. So understand that when it comes conceptually to Bronsted-Lowry acid bases, you guys need to be able to report the conjugate base or conjugate acid, depending on what the question is asking, with the correct formal charge. And if you're giving a reaction, understand that sometimes it is worded, what is the conjugate acid base pair? Let me just write it here. When it comes on wording, I don't want you guys to be confused. If you ever see that the question is worded saying, what is the conjugate acid base pair? overall, what that question is asking is, if you're given a base, what is the conjugate acid that paired with it? Or if you're given an acid, what is its conjugate base? Okay, don't be confused by that wording. That just means like, how are they paired? And remember that the answer is going to be either a base with its conjugate acid, or an acid with its conjugate base. Okay, so you just have to look at the choices that you're presented with. Excellent. So let's move right along and talk about now. Sorry, I'm sneezing. Wait. Yeah. Thank you so much. I may mute myself if I start sneezing constantly. But let's move on to the next section in chapter 9, which is chemical equilibrium. So what is equilibrium? If you have a reaction and the reaction has reached equilibrium, understand that no further changes in the concentrations of reactants and products is going to occur. So what does that mean? In these reactions, the way that they are written, you're going to see that they're going to be symbolized specifically by just having two arrows, one in the forward direction and one in the reverse direction. So in a system that is in equilibrium, understand that constantly the reactants are going to go to products and the products are going to revert to reactants. And that is a true system. You may be curious of like, why would that happen? Well, many systems that actually happen in the body, specifically we're going to see later in the chapter, buffers, actually have these dynamics in order to control changes that may happen in the environment. Now, understand that the arrow that is going forward, that means that that's the forward reaction. The arrow that is going from product to reactant, that is the reverse reaction. In the right side of the slide, you can see here that there is a plot as time progresses and we compare the concentrations in moles per liter of reactants and products. We can see that overall the concentration of the reactant is going to decrease and then is going to stabilize. But that makes sense. Reactants are going to product, right? And then we can actually observe that the products are going to be increasing. And at some point, they're going to flatten out, right? So in that flattening portion of this graph, that's where the equilibrium is actually occurring. Now, there is an important principle that we must learn when it comes to equilibrium reactions. And that specifically is called the Le Chatelier's principle. The Le Chatelier's principle states that when a system is in equilibrium and all of a sudden that equilibrium is disturbed, what the system is going to do is actually adjust the rates of the forward and reverse reaction in order to not be stressed anymore. Because overall, a system that is in equilibrium wants to reestablish its equilibrium. One of the, I think, more successful analogies that I have seen in order to explain Le Chatelier's principle is utilizing a water tank, okay? So let's observe how this example of a water tank can actually allow us to understand Le Chatelier's principle at work a little bit better. So let's say that we have a system in equilibrium, which is specifically what we have in this first image. We can see that specifically we have two compartments to our system, tank A and tank B, right? The system is equilibrium. You see that there is some degree of liquid in both compartments and it is leveled. Let's say that you, quote unquote, stress the system because you added water to the first compartment, to tank A, okay? So overall, if you actually add more water to tank A, the system, in order to regain equilibrium, you can see from the arrow, is going to basically make water flow into tank B in order for the system to regain equilibrium. It is actually reestablishing a new equilibrium. And we can see that as a result, now both compartments are going to have liquids, but overall, in order to create this new equilibrium and for that equilibrium to be reestablished, we have the water flow increase from compartment A to compartment B. So when it comes to Le Chatelier's principle, there are many things that affect the equilibrium of a reaction. Pressure can change it, temperature can change it, the state of matter of the reactants and products can affect it or not affect it. But in this class, we are going to learn specifically how the concentration of reactant and the concentration of product are going to be affecting an equilibrium system, okay? So remember, when we alter the concentration of a reactant or a product of a system in equilibrium, the rates of the forward and reverse reactions will no longer be equal, and something has to adjust in order to reestablish a new equilibrium in the system. Now, to summarize the observations for Le Chatelier's principle, when we have the addition or removal of product, all of this has been summarized in the following table. So this table is actually illustrating what happens when the stress is adding reactant, removing reactant, adding product, or removing product. So I'm going to suggest that for the exam that you guys have upcoming, just have this table available for your next exam. Okay, so just have it ready. So you're able to utilize it to understand, okay, depending on my stress, what's going to be the effect on the rate, which is what the second column doing, or the shift, that means the arrow. Is it going to move towards the reactant or is it going to move towards the product? That's what the third column is saying. Let's do an example to actually explore these concepts, okay? So here you can see that we have the following reaction. Let me just enlarge it so we can see the reaction. So we have CH4 plus H2S. That, as you can see, this is a double-headed arrow. So this also means forward and reverse. So it means the same thing. It's the same thing. And then those two gases, when combined, they're going to make CS2 and is going to make specifically 4 H2s. Notice that all of the components here, the reactants, the products, are in gas form. The other state of matter that we can have in reactions that undergo equilibrium is going to be aqueous. If you have anything in solid or liquid form, let me just write a note. Any substance in liquid or solid form in an equilibrium reaction do not affect the equilibrium. So this is for any of you that maybe in the future you have to take other chemistry classes. Understand that whenever we have equilibrium reaction, any reactant or product that is in solid form or liquid, it doesn't affect the equilibrium reaction. It is because those substances are considered to have constant composition, and anything that has constant composition basically doesn't affect the equilibrium reaction. Only things that are gases or aqueous are going to affect the equilibrium reaction. So just keep that in mind in case you have to take other chemistry classes. But we can see here that we have a series of statements, okay? And then based on that, we're going to see what happens overall to them. In order to understand this, I'm just going to label the different stresses with a letter. So this is going to be A, this is going to be B, this is going to be C, this is going to be letter D. So it is important that you remember and recognize, okay, what is happening here overall. So as you can see here in letter A, it says, decrease the concentration of dihydrogen sulfide. Dihydrogen sulfide is going to be H2S. So which letter corresponds to that statement? A, B, C, or D? Let's put it in the chat. Decrease concentration of H2S. So H2S, is that in the reactant or the product? That's in the reactant. So based on the letters for the stress, are we adding reactant, removing reactant, adding product, or removing product? Which letter would that stress correspond to? A, B, C, D. I agree with Maria, letter B, because we are removing a reactant, okay? So H2S is in the reactant side. It says decrease the concentration of H2S. That means that we are removing a reactant. So this is letter B. So overall, if we're removing a reactant, let me go back to the water tank example that we had here. So if we think about, let me just erase some of these markings. If we have our water tank, let me maybe take an image of this. Oh, why you don't want to do that? Right, I know what I'm going to do. And just take this, copy. So if I use my water tank analogy here, letter A establishes that if I write my reaction here, on this side is going to be the HCH4 gas plus H2S, and on tank B is going to be CS2 plus H2, okay? Decreased concentration of dihydrogen sulfide means overall that I open a compartment here and then water is going to rush out. We can see that in letter B, it says that it's going to decrease the rate of the forward reaction, but that kind of makes sense because overall, in order to regain a new equilibrium, water has to move in this direction. So you can see here that this is going to say, oh, we're shifting towards reactant. And that makes sense because as water is escaping, it needs to move from B to A in order to reestablish a new equilibrium. Okay, let's go over letter B. Increase concentration of H2. What letter would that correspond to? Hydrogen gas. That's H2. If we are increasing the concentration of H2, what are we doing? Add reactant, remove reactant, add product, remove product. Give me one moment. So like you guys said in the chat, we are adding product. So in this case, we can see that that's going to be kind of like, this is the system. We open this compartment. We add more product. The level of the water in compartment B is going to increase. And overall, what's going to happen is that it has to go towards the reactant, okay? Like you see here, it's going to shift the direction towards the reactant in order to reestablish that equilibrium. Let's do at least one more. Increase the concentration of methane, CH4. What letter does that correspond to? If we increase the concentration of CH4, excellent. Yes, this is going to be letter A. Letter A says that if I add more reactant, then I'm going to increase the rate of the forward reaction and the shift is going to be towards the product. So again, when it comes to this question in the exam, understand, have this table ready. Now, let's move on to the next concept of chapter 9, which is going to be pH and the pH scale, which is going to be the lab that I'm going to be posting next week for you guys to complete. It's going to be part of the lab kit. Now, let's understand that pH is actually a indicator that is going to allow us to understand what is the acidity of a solution. pH is actually in a range, okay? It goes from 0 to 14. Are there things out there that have a pH that is negative? Of course, but we typically don't see them here in class. Now, understand that in this pH scale, okay, anything that has a pH that is less than 7, that is considered acidic. Anything that has a pH of 7 is neutral, and anything that has a pH of greater than 7 is considered basic. And you can see the ranges right here in the notes. Now, let's understand that when it comes to pH, it is actually detecting the concentration of protons that you have in a particular solution. And believe it or not, maybe some of you knew, but if you didn't know, let's just see here. pH value is actually found in many things that we are exposed to. So you can see here on the image that we have on the right side of the slide, how we have a range of different pHs, and we can see some things that we may be aware of or not that we have in everyday life. So as you can see, lemon juice is acidic at a pH of 2.2. Sodas or carbonated beverages have a pH of 3, so they're also acidic. Bread actually has an acidic pH of 5.5. Milk is actually acidic with a pH of 6.4. You can see that pure water has a pH of 7.0. Now, drinking water is slightly basic because it has a pH of 7.2. Our blood is actually slightly basic. You can see that it has a pH of 7.4. Seawater actually has a pH of 8.5, so it's actually a base. And you can see here that many detergents are considered basic just because they have pHs higher than 7. Now, when it comes to pH, we actually have several ways in which we can detect pH. Now, in the laboratory, we actually have an instrument that you can see it here on letter A. This is called a pH meter. So in a pH meter, understand that overall we have this part of the pH meter that I'm circling in yellow. That's the probe of it. And once the pH meter is calibrated, the tip of that probe, when you put it in any solution, it can actually detect on the screen what is the pH of a solution. It depends on the chemistry course that you're taking, but pH meters are commonly used in general chemistry. So if you have to take the full year of general chemistry at some point, I don't know, that this is an instrument that is commonly used. Other times we actually have paper that has been stained with a particular molecule that, depending on the amount of H plus that you have in a solution, is actually going to change color. And that is known as a pH paper. You can see specifically that this pH paper here have different colors, and it actually goes from pH 0 all the way through 11. And whenever this strip of paper is actually placed in a solution, it will change color. And when you change it, and when you compare it to the colors that you have here, then you can tell, oh, this is the pH of the solution. Now, there are actually molecules that exist in fruits and vegetables that can do the same thing that pH paper can do. And the last one that we have here, oh, let me just write here, pH paper. And then lastly, what you see here is specifically an extract of purple cabbage juice. Put a 1 in the chat if you have ever worked with purple cabbage juice as a pH indicator. No, this is something that you guys can actually try at home. It is a lot of fun for me, specifically in the holidays. If I'm in groups, you know, gathering with friends, usually the kids are like, oh, what can we do? And they're bored. I was like, let's play with purple cabbage juice. And in purple cabbage juice, there is a molecule that is actually called a flavin. It is specifically anthocyanin. And this molecule is what's responsible for purple cabbage to give the colors that you see in the test tube rack in the back. So in purple cabbage, this is the color that it does around pH 7. These colors are going to be for the basic solutions. These are going to be for the acidic solution. So typically what I do is like I just boiled some purple cabbage in distilled water, and that's what you see in the beaker. And then from there, depending where we're gathering, I just, you know, with the kids take different household products. I was like, okay, let's investigate what is the pH. And believe it or not, like, you know, sometimes people are just interested in science and they're like, oh my God, I learned something today that, you know, just like we saw based on the pH scale, bread is this, milk is that, soda is that, gum, candy. So it's actually, you know, a little bit of fun for those kids that may be, or adults, it doesn't matter, that are interested in science. So purple cabbage, this is something that is relatively inexpensive. Purple cabbage is found at grocery store. Yeah, I agree. It's like chemistry magic trick. And then sometimes the kids are like, oh my God, look, I am drinking like pink milk. And people are like, huh, what? I was like, it's just a little bit of purple cabbage. Now, the smell is the only thing that gets people because, you know, boiling cabbage has a particular odor to it. But in terms of looking at the color changes is a lot of fun. So understand that purple cabbage can also detect what is the pH of different substances. Now, pH can actually be calculated. And when it comes to calculations of pH, understand that the equation for pH is this one that we have right here. Because pH tells you how acidic something is actually calculated by looking at the negative log of H3O+. Understand that the hydronium ion, or H3O+, is the same thing as saying H+. The reasoning behind it is because H3O+ is actually a resource of H+. So when H3O+ acts as an acid, it's going to give away an H+. So that's why sometimes interchangeably in the pH equation, you may see hydrogen ion concentration, which is here, or you may see that the question is worded hydronium ion concentration, which is this. So understand that they are going to be a source of H+, so it doesn't matter which one is in the question, you will be using the pH equation to find out what is the pH of a particular substance. Now, when it comes to this, remember that the pH doesn't have a unit. The pH is just a number in a scale. This scale is logarithmic. That's why we're taking the negative log of the concentration of that H3O+. And specifically, it is important specifically for this concept that you guys know how to enter these numbers on your calculator. If anybody has issues on how to enter these numbers into your calculator, please reach out, come to office hours next week. I'll be more than happy to help you how to do the numbers for calculating pH or for any of the calculations that we need to do based on this concept, okay? So when it comes to this, let's actually do some practice problems in order for us to understand the different questions that we may encounter in assignments or the exam next week when it comes to pH. So when it comes to pH calculations, there are going to be 3 specific equations that you guys need to know. So let me just put it here. You need to know for exam. And these are the different equations. So let me just put them in letters. So this is equation 1, this is equation 2, this is equation 3. Equation 1. This equation is specifically going to be used when you're given a concentration of H+ or H3O+ and you need to calculate the pH, okay? So basically for this equation, H+ concentration or H3O+ concentration is given. And you need to calculate pH, okay? Equation number 2. You are given pH and you need to calculate the concentration of H plus, in other words, the concentration of H3O plus. Remember that H plus concentration is always going to equal the concentration of H3O plus. Okay. And lastly, we have a particular equation that is actually looking also into the concentration of OH. Remember that OH is the base, okay? So we can see here that this equation can be isolated into two more, which I call 3A and 3B, in which I say, okay, if I need to calculate the concentration of H plus, because I'm given the concentration of OH minus, I'm going to do 1.0 times 10 to the negative 14 divided by that concentration of OH to find the concentration of H plus. Similarly, if I'm given H plus, but I'm interested in finding the concentration of hydroxide, just because I want to know how much base is in a particular solution, then I'm going to do 1.0 times 10 to the negative 14. And then I'm going to divide that by the concentration of H plus, okay? Because it has been given to me. So utilizing these four equations, let's actually do some example problems in the last 10 minutes of class to make sure that we know how to utilize them, okay? Let's go specifically through the following. In the first problem, it says, if the H plus concentration is 2.1 times 10 to the negative 12 polar, what is the pH? So we are given H plus, and we need to find pH. Which equation am I going to use? 1, 2, 3A, or 3B? Let's put it in the chat. Which equation do I need? I agree with Maria. We are given H plus, and I need to calculate pH. So I need equation 1, because this is given, and then I need to calculate pH. So I need to use equation 1. So I'm going to say, okay, pH, which is what I'm trying to calculate, is going to be the negative log of 2.1 times 10 to the negative 12. Understand that there's actually logarithmic significant figure rules, but when it comes to it, to be honest with you guys, I just ask you, express your answer in the following number of sig figs, so you guys don't have to actually think, because they are actually a little bit complex when it comes to the rules. So in exams, I actually ask you, or I tell you how many sig figs you need to round your answer to, okay? So for example, here, we're going to round to 2 decimal places, okay? So I put in my calculator 2.1 times 10 to the negative 12, and then I take the log, and I do the negative. So overall, I get a pH value of 11.68, okay? Now, since I got a pH of 11.68, is this acidic, basic, or neutral? At a pH of 11.68, is that acidic, basic, or neutral? I agree. This is considered basic, okay? Because remember, it's higher than 7. Let's look at problem 3. What is the hydrogen ion concentration of a solution with a pH of 8.25? So if I'm given pH and I want hydrogen ion concentration, which equation am I going to need? 1, 2, 3A or 3B? I'm given pH. So if I know the pH, which equation do I need? Excellent. I need equation 2. I am given pH. I want H plus concentration. I have equation 2 that will tell me exactly that concentration of H plus equals 10 raised to the negative pH, which means 10 to the negative 8.25. So I write in my calculator, I enter that. And then I find specifically 5.6234 times 10 to the negative 9. So this is 5.6. If I need to express it as 2 sig figs times 10 to the negative 9 molar. Okay. So again, when it comes to these equations, if you don't know how to enter this in your calculator, I'll be more than happy to help you and show you how to do this in your own calculator, because I know sometimes students don't know how to enter this in the calculator, and it is crucial for this concept. So when it comes to this, let's do problem 5. In problem 5, notice that we're trying to calculate the OH minus concentration. And what we're given is pH. Out of the equations that I gave you, is there one that directly relates pH to the concentration of OH? Yes or no? Which equation relates directly OH and pH? Okay, I agree with you that 3A is necessary, but where do I enter the pH? I'm saying like one equation only that I can just enter the number given to me in pH, and then I find OH concentration. And most likely is 3B because I'm trying to find OH. Remember that for those of you that are like, I don't know how to pick equations, this is what you're trying to find always. And most likely these things is what is given. So again, do we have a single equation in which I can plug in the pH given and it's going to put out the OH concentration? Yes or no? I disagree. We don't have an equation where we put in the pH and we get OH out. There's no, if you can see here, this is what is given. This is what you need to find. This is what is given. This is what you need to find. So none of these equations, I can just plug in the pH and get the OH out. The only thing that we could do is actually use a pair of equations to actually determine the values for the question that we have. I agree with you, Vanessa, exactly. We need to use two equations. First, if you're given the pH, you need to use equation 2 to find H plus, and then finding H plus, you can find OH by using equation 3B. So that's exactly how we solve problem 5, okay? First, we're going to use equation 2, which establishes that the concentration of H plus is going to be 10 to the negative 5.22. So when I plug this into my calculator, this is specifically 6.0 times 10 to the negative 6. And then when I use equation 3b, the concentration of OH minus is going to be 1.0 times 10 to the negative 14 divided by that 6.0 times 10 to the negative 6. And when I do that, 6.0 times 10 to the negative 6, 1.0 times negative 14 divided by 6.0 times 10 to the negative 6, then I find that my concentration of OH is 1.7 times 10 to the negative 9 molar, which if it's concentration, then the result is in molar, okay? So next week on Tuesday, we are going to review these equations. Again, get more practice so you guys know how to do the calculations for pH. And this is the last concept that is actually going to come in the exam next week. Thank you guys so much for coming. Have a great Thanksgiving. And I'll see you guys next week.